Stanford University.
All right. As I said, the basic tool of the trade is quantum field theory. And that is what we're going to spend a little bit of time learning. I'm going to teach you a very elementary version of what a quantum field is, I think, tonight. But I do want to get up on the blackboard some basic mathematical facts, just to review and to remind you. This is too elementary to be a serious part of this class at this point, but I do want to get it up there. The first mathematical set of facts does have to do with waves. Waves are, of course, an example of fields, field configurations. Fields are things which vary throughout space. Waves are particular kind of configurations in which the fields are moving in a wave-like motion. And waves and particles are closely connected through the link of quantum mechanics. I am not going to teach a quantum mechanics course this quarter. So if your quantum mechanics is fuzzy, uncertain, go back to the lectures on quantum mechanics. The two sets, there was a class called Quantum Entanglement, which we'll get up there hopefully soon, and another class just called Quantum Mechanics, and that is the basic starting point for what particle physics is. Also special relativity. But let's just review very, very quickly one mathematical fact which comes up over and over and over and over again, just what the relation between sines, cosines, and exponentials. Everybody, probably most of the people here know this, but I just want to get it up on the blackboard. For future reference. Okay. Let's remember what an exponential is. An exponential is an exponential function. It has the form e. E is a certain number to the alpha x. Alpha is a number. It could be any number, real or complex, or pure imaginary. And e to the alpha x is a function of x. An exponential is a function which grows, in this case with respect to x, by an amount each separate little interval of x, it grows by an amount proportional to itself. For example, a population of a petri dish. The increase in the population is proportional to the population itself. And so the hallmark of an exponential, let's call this f of x, is that the derivative of f of x with respect to x is proportional, in this case with the proportionality factor alpha, times f itself. The rate of change is proportional to f itself, and such a function is called an exponential, and it's denoted e to the alpha x, or something. It can be a number times e to the alpha x. Okay, that's the hallmark of an exponential. Now, let me remind you of some facts about sines and cosines, and then put them together very quickly. Sines and cosines, you know what they are. They're functions which oscillate like this. That's sine of x. And cosine of x is exactly the same function, except shifted over by 90 degrees, and it looks like that. And I'm sure you all know this. I won't bother going into detail. But the important thing about sine of, let's say, kx, let's call it sine of kx. Sine of k, where k is a number, any number, real number in this case, times x. Could be positive, could be negative. And the other function of interest is cosine of kx. All right, sine of kx and cosine of kx can be differentiated, both of them, and I'll just remind you what the derivative is. No, you'll remind me. What's the derivative of sine of kx with respect to x? The sine of kx with respect to x is equal to k times cosine kx. And the derivative of cosine with respect to x is minus k sine kx. So neither one of these is an exponential. Neither one has the property that when you differentiate it, you get something back proportional to itself. they have the odd property that when you differentiate one, you get something proportional to the other, in one case with a minus sign. Cosine kx, thank you. Cosine kx. So you differentiate this one, you get the other one, you differentiate the other one, you get minus the first one. All right, so out of these two, you can now build a exponential, but it's an exponential of an imaginary thing. So let's just do it once and be done with it. If you take the combination cosine kx plus I sine kx, I being the square root of minus 1, and you differentiate it with respect to x, what do you get? You get from cosine, you get minus sine kx plus I'm sorry, minus k sine kx plus ik cosine kx. Did I do it correctly now? I think I did. Which is, just spend a couple of minutes doing the algebra, I times k times the original thing back again, cosine kx plus I sine of kx. In other words, to make a long story short, cosine kx plus I sine kx is the function e to the I kx. When you differentiate it with respect to x, you get ik times the same thing. All right, so that's an important mathematical fact that comes up over and over again. Sines and cosines are, of course, the functions which describe wave-like oscillations, either oscillations with respect to space. If x is a space coordinate, there's an oscillation that oscillates with space. If x happens to be time, it corresponds to an oscillation with respect to time. All right, we'll come. Now let's consider in a little more detail. Wow, not so much detail, but just quick review. All right, we have a wave. The wave is moving past us. It has a certain frequency, and it has a certain wavelength. Let me just remind you of the connections, because we'll use them. We can call f the frequency. It's the number of cycles that pass you every second. Frequency, and it's measured in cycles per second. C stands for cycles per second. A cycle is one full oscillation of the wave. Another definition. Now this is definition. Omega is another form of the frequency. It's the angular frequency measured in radians per second, and it's just equal to 2 pi times f. So f and omega are the same thing except for a factor of 2 pi. And I may go back and forth between them, try to keep equations as simple as possible with as few factors of pi. So sometimes I may use omega, sometimes I may use f. Okay, lambda is, of course, the wavelength. And now for a light wave moves at the speed of light. Because it's moving past you with the speed of light, the wavelength and the frequency are related. And they're related by the formula. The wavelength is the distance traveled in one full cycle. And if you multiply that by the frequency, that gives you the speed of light. That's the velocity. The frequency is how long, well, the inverse of the time that it takes to go one full cycle. So this is a distance divided by the time that it takes to go one full cycle. And for a light ray, this is c. If it's a sound wave, then you put the speed of sound there. If it's a water wave, you put the speed of water waves there, or whatever it happens to be. But we'll be, of course, particularly interested in light waves. Now, that's one set of equations. The other set of equations that we discussed last time, just quick, brief review of last time, is the equations of quantum mechanics which relate wave-like motions to particles. And we're not going to go in heavy depth into the explanation of these equations. For that, you go back and open up the lectures on quantum mechanics. But nevertheless, I'll try to be as complete as possible, or at least as self-contained as possible. The important thing when going to quantum mechanics is a new number, Planck's constant. It comes in two separate notations. There's the old Planck's constant, which was Planck's original notation. And then there's the new Planck's constant, which is the same as which is the same as the old Planck's constant, except for a factor of 2 pi. And that 2 pi is put there so to save 2 pi's in somebody else's equation. But they always come up, and there's just no escape from 2 pi's. You're always going to have them. But the other definition is h bar, and that's the old Planck, that's the new Planck constant. That's the old Planck constant divided by 2 pi. I will simply save 2 pi's by sometimes using h and sometimes using h bar. Try to keep the number of 2 pi's to a minimum. Now, lambda times, let's see, okay. Yeah. That's not an equation, that's just a definition. And what is h? H is a number, which is a tiny, tiny, tiny number. Anybody remember what it is? 6 times 10 to the minus something. 34 or something? In some units or another. Oh, that was an interesting question. In my email, it showed up somebody questioning whether the origin of the unit meter, pointing out, let's see, what is the meter? The meter is 1/40,000,000th of the way of the circumference of the Earth. And said, no, I was wrong. It didn't have anything to do with this. It's 1/40,000,000th of the... Do you think that somebody just came along and said, let's define a unit which is 1/40,000,000th of the circumference of the Earth? No, of course not. That unit had been in use. I don't know whether it was called a meter or not. In England, it was called a yard. But why 1/40,000,000th? Why not 1/40,000,000,000th or 1/40? Well, because you wanted some unit that was easy to deal with for a human being, good to measure rope with, good to measure cloth with, whatever. And I do believe that the origin of a unit which is about the length of a human being's arm predated knowledge about what the circumference of the Earth was. Anyway, which in fact was known for a long time, but yeah. In any case, in standard units, meters, seconds, and kilograms, h bar is a very small number. Do I have it right? Something like 10 to the minus 34? Yeah. 1 point. That's little h bar. That's h bar. H is 6 times 10 to the minus 34, or whatever. And c, of course, is 3 times 10 to the 8th meters per second. Right? 3 times 10 to the 8th meters per second. Right. Okay, so this is just a definition of some number, or the definition between a relation between two numbers. But the fact is that the energy of a single photon, a photon associated with a wave of a given wavelength, and therefore a given frequency. Notice this equation here tells you the relationship between frequency and wavelength. Frequency and wavelength are inversely related. The bigger one is, the smaller the other is. The energy of a single quantum, energy. Now, this is not the energy of an electromagnetic wave. This is the energy of one quantum of the electromagnetic wave. That's equal either to h bar omega, where omega is the frequency of the wave, the angular frequency of the wave. Incidentally, the frequency of an electromagnetic optical, an optical wave, one that you can see with your eye, is very, very rapid, something like about 10 to the 15th cycles per second. Do I have that right? About 10 to the 15th cycles per second. So typically omega is very, very large, 10 to the 15th blah, 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 per second. But h bar is more than small enough to make the energy of a single quantum very, very small. If you multiply these two in the units that we've been using, you get the energy in joules. And you find out that the energy in joules is very small, 10 to the minus 19th or something like that. So it would take a huge number of optical photons to add up to any appreciable macroscopic conventional energy. All right, so the energy, and this of course is also equal to the other Planck's constant times the other frequency. So they're the same thing, just two different notations. All right, now let's talk about momentum. Let's remind ourselves about momentum. Energy, incidentally, and momentum are especially interesting because they're conserved quantities. They're conserved. Total amount of energy is conserved. Total amount of momentum is conserved. And therefore, they're good bookkeeping devices, good for writing balance equations and useful, among other things, besides being deep. Momentum is a vector. It points in a direction, points typically in the direction of motion of an object. It's defined by being conserved. Okay? But having said that it's defined by being conserved, by the fact that it's conserved, we count it and so forth, we can ask what is the momentum of various kinds of objects in nature. And the first thing we can write down is the momentum of a non-relativistic object. Non-relativistic object just means one moving slower than the speed of light. Oh, a lot slower than the speed of light, a lot slower. The momentum of such an object is proportional to its mass times its velocity, and its velocity is also a vector. All right. If I give you any pulse of radiation, electromagnetic radiation, and it's all collimated along a given direction, not a dispersed wave which is going out in a variety of different directions, but in which everything is lined up and collimated along an axis, then this is non-relativistic. The opposite extreme is super-relativistic. In other words, moving with the speed of light. Now, this formula is not right for moving with the speed of light. You could plug in for v, the speed of light, but what do you plug in for m? Remember, I told you, m is always, by definition, the rest mass, what we used to call the rest mass. And a photon doesn't have a rest mass. Okay, its rest mass is 0. You try to bring it to rest, it has nothing. But this is not the right formula. Nevertheless, the right formula has a look which looks a bit like this. If we were to have used inappropriately E equals mc squared. Now, mainly I'm using this for units in order to get units right. Energy is mass times velocity squared. Then, of course, mass would be an energy divided by the speed of light squared. All right, now if I, as I said, inappropriately ascribed to a photon a mass equal to its energy divided by c squared, the energy of the photon divided by c squared, and then said that the velocity of the photon was c, in fact, more or less somewhat accidentally, I would get the right answer that the magnitude of the momentum, this should be read as the magnitude of the momentum.
Or you could just write like r hat.
Yeah, right. But the magnitude of the momentum is the energy of the photon or the energy of the electromagnetic wave. For any electromagnetic wave all moving in a constant direction, the direction of the momentum is, of course, the direction of motion of the wave. That's easy. But the magnitude of the momentum is the energy of the wave divided by the speed of light. From that, we can say, supposing the wave consisted only of a single photon. Now, are we using it legitimately? Yeah, you get the right answer. What is the momentum of a single photon? And to get the momentum of a single photon, you just plug the energy from here into the formula for the momentum. So let's do that. The momentum for a single photon. Well, let's do it over here. Momentum of a single photon, let's write photon over here. Can that be read? Everybody read that? The momentum of a photon. And I'm concentrating now on its magnitude. Incidentally, the double bar here means the magnitude of it. The direction is along the direction of the beam of light or along the direction of the photon. Let's plug it in. The energy, let's see, let's use this formula over here. H times frequency. Energy is H frequency divided by C, right? What's the frequency divided by C? Right, or one over the wavelength or 1 over the wavelength? Frequency divided by C, I've divided by C, is equal to 1 over lambda, right? Did I get that right? Yes. Frequency divided by C is 1 over lambda. So this is just the equation that the photon momentum in magnitude is equal to Planck's constant, that makes it small, times the frequency divided by C, which is divided by the wavelength. So the smaller the wavelength, the larger the momentum of the photon. That's a pattern, and it's in some sense the most important fact coming from quantum mechanics about particle physics, that if you want short wavelength for the purposes of studying very small objects, the price that you pay is you have to put a lot of momentum in. Question? Yeah.
The formula E equals H bar omega.
Yeah.
Is that fundamental, or is that derived from some symmetry that we're going to learn later on?
It derives from the quantum mechanics of a harmonic oscillator. So the place to look it up is on previous lectures about the harmonic oscillator. I will make use of those lectures, but that's where it comes from a deeper point of view. We'll come to the right statements, although not the demonstration of them. Yeah. Yes.
And just to touch on the amplitude, since we have waves in a group of photons or an electromagnetic wave, it has an amplitude, and all waves have amplitudes. But a photon in and of itself, we haven't talked about its amplitude. Maybe you can touch on that.
Let me answer the question now. I knew it was there, and I was waiting to get to the right point, but why don't I just say it now? Right. An electromagnetic wave, or any other wave, has several features, one of which I have not written down here. It's the amplitude of the wave. Now, the amplitude of the wave, well, okay. Here are two waves with the same frequency, the same, in every respect the same, except that and here's another one. One of them is just some small number times sine kx, for example. Maybe the small one is just sine kx. The other one is a great big numerical multiple, which I'll call A times sine kx. They're exactly the same, except one is much stronger than the other. It's got a larger amplitude. A is the amplitude of the wave. And now the question is, in photon language, what is the meaning of the amplitude? Or another question you could ask is, what is the amplitude associated with one photon? Now the question is a little bit ambiguous because quantum mechanics always has uncertainties. Technically it has uncertainties. and you can't measure everything simultaneously. For example, you can't measure both the amplitude and the phase of the wave. The phase of the wave is where it's located, but never mind that. Or there's a sensible order of magnitude question. Order of magnitude, what is the amplitude that's associated with a single photon, for example? Okay, the answer is the following. The energy of a wave, now this is a completely classical statement, the energy of a wave is proportional to k times the square of the amplitude. For example, if this was the electromagnetic field, let's say the electric field or the magnetic field associated with an electromagnetic wave, what's the energy of an electromagnetic field? It's proportional to the square of the electromagnetic field. So typically, the energy of a wave is proportional to the square of the amplitude. All right. If you take, good. Now, the energy of the wave is also proportional to the number of photons in that wave. So here I've described for you some features of a single photon, but a wave of light consists of many photons. Let's suppose the number of photons in some wave of light is n. Then the energy is proportional to n. In fact, the energy will be n, the number of photons, times h bar omega. So that means that there's a proportionality between the square of the amplitude on the one hand and the number of photons in that wave, let's just call it little n. The precise, exact, detailed connection I'll work out for you another time. But the square of the amplitude of the wave is proportional to the number of photons. Now, there's a factor of h bar in there because the square of the amplitude is the energy, and we should have an h bar omega in the energy. So the square of the amplitude is proportional to h bar and n. Now, of course, the point is that h bar is an extremely small number. This is the energy of the wave. Another way of writing the energy of a wave with many photons. Not a single photon, but many photons. All right, now you say, well, look, this is a terribly tiny number. How can you get any appreciable amount of energy in an electromagnetic wave? Well, the answer is by having a lot of photons. So a typical electromagnetic wave that carries an appreciable energy has an enormous number of photons to overwhelm this factor of h bar. But the amplitude, if you like, A, is proportional to the square root of the number of photons. So that's the missing wave characteristic that I didn't write down here. And as I said, it is proportional to the, yeah.
I think that there's a common confusion about the oscillation when you see a diagram of the E and the B fields that are perpendicular sine waves. And there's a temptation to think of that as a spatial, the height of the sine wave as being distance that the photon is wiggling in space or something.
No, right, okay, right. Okay, so here's a wave. It's moving down the x-axis. What's plotted vertically here is not the y-axis or the z-axis. What's plotted vertically? The electric field. Right, so this is not a plot. There's only one of the directions here corresponds to space. The other direction, of course, corresponds to the electric or the magnetic field. I think that's what you were asking me to clarify, and properly so. Now, of course, the wave could be oriented in any direction. That way, that way, that way. And the momentum carried by the wave is along the axis that the wave is moving. Yeah.
You say the number of photons in the wave, you mean within one period of the wave?
Well, I'm sorry, I couldn't hear you.
You mean the number of photons within one period?
Let's say within one period, yeah. Yeah.
Because A squared is like the power density rather
Yes.
than energy, right?
That's right. So that's why it is necessary to say within one wavelength. That's right. Well, the proportionality, I purposefully wrote proportional to here. If we were talking about 2 wavelengths, 3 wavelengths, 4 wavelengths, of course the answer would. But yes, you got the right idea.
So does that mean that the amplitude of a single photon is meaningless?
Well, order of magnitude, it's given by this formula with n equals 1. But yes, in some sense it is meaningless. It's as meaningless for an electromagnetic wave. The electromagnetic wave has both a magnetic field and an electric field. Now, the magnetic field and the electric field are related to each other by a relation which is similar mathematically to the relationship between the position of a particle and the velocity of a particle. And those are things which cannot be measured simultaneously. They are, the uncertainty principle prevents you from knowing both of them. And in the same way, there's an uncertainty principle between electric field and magnetic field that prevents you from knowing both of them. So yes, there are limitations on how well you can know the amplitude. But as an order of magnitude statement, this is correct. We'll try to do better as we go along. We're sort of getting into the subject of quantum field theory, which is a difficult and abstract subject. Okay. I wrote down some equations here which are true for photons. Some of them are true for any particle, others are not. All right, the definition of frequency, that's a general definition, omega being 2 pi f, that's perfectly good. Lambda equals a wavelength, that's a definition. This is true for waves which will move with the speed of light. So it would not be true for a general wave. Let's put something around those equations which are not expected to be of great generality. By great generality, I mean they would be true for almost any kind of wave or particle, whether or not it moves with the speed of light. This is not so general. This is not so general. Anything that has a c in it will not be very general. When I say not general, it'll be general for anything which moves with the speed of light. Okay, this is general. Now, energy equals h bar omega. That is also a very general fact. This clearly, neither of these. This is specific to things which move with the speed of light. This is specific to objects which move with much less than the speed of light. There's an interpolation in between, which I won't get into now, which is true for things which move with some fraction of the speed of light. Let me see if I can. Where were we? Yeah, we were trying to figure out which equations are of great generality, which are not. This one, hf over c, that contains c in it. That is not terribly general. Oops, where's my blue? Momentum equals h divided by lambda is general. Okay. Now, where this comes from, I'm not going to try to prove these things to you now. I'm just telling you as facts. Go back to your quantum mechanics. Momentum is h over lambda. That's general. Okay, let's use these facts now. Here's the relationship for a photon between, what is it? Between frequency and wavelength. And as I said, it's not very general. What about a slowly moving electron or a slowly moving nucleus, or for that matter, a slowly moving bowling ball? What's the relationship between frequency and wavelength? Can we figure it out? Is there something on the blackboard or something? Do we have to add something else? Question. For an electron, remember, I did tell you last time that electrons are also described by waves, did I not? I told you that you can do interference experiments with electrons. So there is an electron wave. Let's call it psi. And the question now is, what is the relationship between frequency and wavelength? Can we figure it out? Yes, we can, but we need to know one fact about non-relativistic systems. It's the analog of knowing, it is not the analog, it's knowing the relation between momentum and energy. Okay? But for an electron moving slowly, the momentum is not the energy divided by the speed of light. What is it? Okay? Energy is equal to, now we can start at the beginning and write, I mean kinetic energy, 1/2 mv squared. And the momentum, mv, p equals mv. So we can solve for the velocity, p over m. Everything is a vector, but that's all right, we don't, that's all right. And then the energy becomes 1/2 m times v squared, and v squared is p squared over m squared. If you don't know this equation, it's an important equation. It occurs over and over. The energy in terms of the momentum is 1/2 p squared divided by m. People get confused. The m is upstairs when you multiply by the velocity squared. It's downstairs when you multiply by the momentum squared. Okay, now we have what we need to find the relationship between frequency and wavelength. Energy is, where is it? Is h bar omega or h times frequency. Let's use h times frequency. Of a single electron now, we're talking about a single electron, h times the frequency of the wave describing that electron, h times frequency, that's energy. On the right-hand side, we have 1/2. Let's put the m downstairs. And what about the momentum? The momentum is h divided by lambda. So that's h squared over lambda squared. And we can divide this equation by h, and we find that the frequency is 1/2m times Planck's constant divided by the square, this time, of the wavelength. Notice how different it is. Over here, the frequency was proportional to 1/, the wavelength. Here it's 1/, the wavelength squared. Now, you don't have to remember this. You don't have to memorize this. You can always rederive it. The basic ingredients are the equation for the energy and the relationship between momentum, wavelength, frequency, and all that kind of stuff. All right. This is just to illustrate the connections. So that's a non-relativistic particle, one moving slowly. For example, an electron in an atom, the frequency of its Schrodinger wave would be 1/2m times Planck's constant divided by the wavelength squared. Let me slow down now and take some questions.
That would be for any particle, not just an electron.
That is true for any particle as long as it's moving slowly compared to the speed of light. Maybe we should, well, we'll come back and we'll interpolate between the slow and the fast another time. There is an interpolation.
It wouldn't work for neutrino.
Neutrino is, well, it depends on how fast the neutrino is moving. Most neutrinos in nature are moving very fast, with close to the speed of light, very close to the speed of light. So for neutrinos, the speed of light is a good approximation for, but in principle, neutrinos can be slowed down, and if they're moving with very much less than the speed of light, it's the other formula, the non-relativistic formula. Yeah, question?
Discussion about A being proportional to the square root of n. So that's where the electrons all have the same wavelength.
Yeah.
So if they're different wavelengths, then if you take them separately, the different wavelengths.
We'll come back to the relation between amplitudes and quanta soon enough, and That's what the whole story is about, but we haven't gotten,
An electron accelerator, let's say with 20 keV.
we have an accelerator with 20 keV, very low energy
As
accelerator.
an example, is it slow or fast?
Is it what?
Is to consider slow or fast?
For an electron, slow. Slow. All right, all right, good. All right. If you want to know, first of all, let's work in units in which C is equal to 1. In such units, momentum and energy have the same, exactly the same units. Where do we have it? Momentum and energy have exactly the same units if C is equal to 1. If you want to know if something is relativistic or non-relativistic, you want to compare its momentum to its mass. If its momentum is large compared to its mass, it's rest mass. A photon has no rest mass, and so its momentum is always much larger than its mass, and so it's highly relativistic, as relativistic as it can be. The figure of merit, the thing that you compare, is the momentum to the rest mass. So now you have to tell me what's the rest mass of an electron you gave me in keV, okay? keV, kiloelectron volts, is a unit of energy. All right, and remember, energy and momentum have the same units. All right, so what's the mass of an electron? 500,000 electron volts. So 20 keV is a lot less than 500,000, and so that's a slow electron. All right. Any other cookies? Any other questions?
Frequency and wavelength for a real wave are related.
Yeah. Well, by the speed, by the velocity of the wave. Yeah.
So is that equation, the last one you had, can you rewrite it based on speed and get the right equation also?
Yeah, but electron waves do not move with the speed of light. Yeah. So there's no speed. So the question is, can you derive a velocity from this? Yes, the answer is yes, you can, but it won't be the velocity of the electron.
Oh, okay. It would be the velocity of the probability wave or whatever?
Well,
okay.
there are two, there are two velocities that go with waves. One of them is called a group velocity, one of them is called a phase velocity. All right, I'll be specific, since you asked me. If you take a general wave, the wave, let's assume it's a wave packet. Now, a wave packet means that it looks like a wave, except that it's confined to some packet-like structure like that. So it locally looks like a wave, meaning to say a plane wave, a sine or a cosine, but it has an envelope that sort of confines it to some region. Now, in general, depending on the specific nature of the wave, you'll see that as that wave moves, there are two separate velocities associated with it, and they're different. One of them is the overall velocity of the wave packet. The other is the velocity of the crests and troughs, or whatever you call them. And what you would see, if you looked at this wave, let's say, from some other perspective, where you see waves and troughs moving along, is you would see the packet moving with one velocity, but the waves moving through the packet with a different velocity. In fact, typically the wave, the one is called the phase velocity. That's the velocity of the troughs and peaks and valleys. And the other is called the group velocity. The group velocity is the velocity of the whole packet. Guess which one you identify with the non-relativistic velocity of the particle? The group velocity. Okay? And the group velocity is usually slower than the phase velocity. The phase velocity is not got to do with the actual velocity of the particle. Now, there is one special case. The special case is when all waves of all frequencies move with the same velocity. That would not be true for a non-relativistic wave like this. Let's see. The velocity is the frequency times the wavelength, right? So let's look at this. The frequency times the wavelength is just frequency times wavelength is 1 over 2m h bar over lambda. So different lambdas move with different velocities. Right? Different lambdas move with different velocities. And when different wavelengths move with different velocities, you have this situation where group and phase velocities are not the same. For the special case where all wavelengths move with the same velocity, then group and phase velocities are the same. So for a light wave, all waves move with the same velocity. The group and the packet velocity, the group and the phase velocity are the same. That's a special and simple case. All right, but I just wanted to illustrate some of the equations here. And incidentally, this equation over here is equivalent to another equation of physics. Anybody know what it is? The Schrödinger equation. The Schrödinger equation is an equation for a wave, and this tells you the time dependence of the wave, the frequency. This tells you the space dependence of the wave. The Schrödinger equation is exactly an equation for the relationship between the time dependence of a wave and the space dependence of the wave. We will come back to it. But this is just the Schrödinger equation in a slightly disguised form. Or better yet, if you knew the Schrödinger equation and you said, supposing I had a wave of a given frequency that had a given wavelength, what would the equation tell me about the relation between wavelength and frequency? And it would be exactly this. Okay, so that's the Schrödinger equation in a nutshell.
Can the phase velocity go faster than light?
Yes. 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 But the phase velocity, as a rule, carries no information with it. You can't send information faster than the group velocity. The phase velocity doesn't really carry any information with it. So we'll come back to that. It's a technical issue that we don't need to deal with right at this moment. Okay. Let's see. Let's go on a little bit more with waves. There are one or two other concepts about waves that are necessary. And, you know, there's a lot of technical detail that I'm getting into, but every single piece of it is really very central or important. Okay. We will be interested in waves moving in infinite space. But I use the word infinite space, infinity. Computers don't like infinity. And if physics is the art of writing equations that computers can solve in principle, it is necessary to always remove the infinities and write the equations for finite systems first, and then take a limit. All right, so in studying quantum mechanics, waves, quantum field theory, particle physics, and so forth, it's necessary in the back of your mind to get rid first round of everything that's infinite and state the problems as if everything were finite, and in particular, what I have in mind now is the extent of space itself. So one way of, what I want you to think about now is a wave moving in one dimension. 3 dimensions is really no different than 1 dimension, except there are 3 of them. So let's concentrate on one-dimensional wave motion. It could be a violin string, it could be a rope being wiggled back and forth, or it could just be a wave in a mathematical universe of 1 dimension. One way of getting rid of the infinity of space would be to make the wave only propagate on a region of length L. For example, by holding down the wave at this end, holding down your string at this end, just like a violin string is held down, holding it down at this end, you can have all sorts of waves, and the waves move and they bounce off. When they get to the end, they bounce off and reflect, and they go back and forth and back and forth. That's a perfectly good way to describe things. The problem with this kind of, let's call it boundary condition, this is called the boundary condition, namely that waves, when they get to the end, reflect. This is called a reflecting boundary condition. The problem with it is it violates one of the important conservation laws of physics. What would that conservation law be? Momentum. After all, if the momentum of a wave is, it's a vector quantity, it points in a direction. If a wave is moving along this, here's a little wave, it's moving along this axis, its momentum is pointing to the right. When it gets to the end, it bounces off and reflects. So the momentum has changed sign. Okay, the momentum has changed sign, the momentum is not conserved. That's okay. There's nothing wrong with it. You can study it. But if you want to keep track of things like momentum conservation, there's a smarter thing you can do. And it goes as follows. Imagine this line is such that we identify the beginning and the end. Now we can do that by replacing the line by a circle. It doesn't have to be a legitimate geometric circle. Just mathematically, we connect the beginning back to the end. So we go in a cycle. All right, so as we move from here to here to here, we can imagine we start here, move along here, and in this magic line, when you get to the other end, you come back to the beginning. All right? That's a closed circle. I don't want to call it a circle because I don't mean to imply it's a circle in 2 dimensions. I just want to imply that it's periodic. Periodic is the term for this, periodic space. Now you can imagine a wave which is moving along here. And when it comes to the end over here, what does it do? It just keeps going. Right? It just keeps going. It doesn't care about that point. That point is not a special point anymore. And so the wave just keeps cycling around, cycling around, cycling around, and the momentum is conserved. It doesn't suddenly reflect into the other direction. In terms of this picture, you can just imagine when the wave gets to this end, it reappears at this end. And it just keeps going to the right if it were going to the right. It goes to the left if it were going to the left, and just keeps going forever. With this trick, with this mathematical trick of replacing space by a periodic space, we can first of all get rid of the infinity in the size of space, feed it into a computer, and we can get rid of the problem of momentum, of non-momentum conservation. Momentum is now conserved. But there is a cost. I don't know that it's a cost, but it's a fact. The fact is that in such a world, momentum is quantized. Now, I don't mean in the sense that, well, it is that momentum only comes in discrete multiples of a unit. And it's useful to work in understanding quantum fields, their relation to particles, and so forth. It's useful to remember that the momentum comes in discrete multiples of something. So let's see how that works. Well, first of all, it's obvious that the wavelength, an integer number of waves, must fit. Let's give this distance around here a name. Let's call it L. L for length. If it were a circle, it would be the circumference. But let's just call it L. The total distance around from beginning back to beginning again. Call it L. All right? If we're going to put a wave in there, and let's say now that it's a wave, a sine or a cosine wave or whatever, an integer number of wavelengths has to fit onto the circle. That means that the wavelength has to be equal to the length around divided by an integer. Okay, divided by an integer. So the wavelength must be the total distance around divided by some integer. I don't want to call the integer n. Let's see. I'll call it capital N. Capital N. Little n will be reserved for something else. So the wavelength is necessarily the total distance around divided by n. Now that means the wavelength comes in discrete possibilities. It can be L, it can be L over 2, it can be L over 3, it can be L over 4, but it can't be L times the square root of 2 or L divided by the square root of 2. An integer number of waves just won't fit in here. In other words, if you tried to put a wavelength of the wrong wavelength in here, by the time you got back, the wave wouldn't match with what it was supposed to be at the beginning. Okay, so that tells you that wavelengths come in discrete possibilities with the integer appearing in the denominator. Now, we had an equation here somewheres for momentum in terms of wavelength. What was it? Momentum was equal h bar. Yes, h over lambda. P is equal to h over lambda. So now this is also telling us that momenta come in discrete possibilities. The momentum of any quantum must satisfy the constraint that it's h divided by an allowable wavelength. So the allowable momenta of quanta, the allowable momenta of electrons, the allowable momenta of photons, the allowable momentum of anything in this one-dimensional world has to be h divided by, okay, let's work it out. That's h divided by lambda. That means n divided by L. I turned lambda upside down, n over L. And what does it say? It says the momenta come in discrete multiples of a basic unit, and the basic unit is Planck's constant divided by the total distance around. There's a neat fact. If you put a particle and you put it, if you put a particle on a wire, and the wire is a circular wire, a bead on a wire, that bead can only have momenta which are discrete multiples of 1 over L, not n over L. N is the multiple. 1 over L, 1 over the length of the wire. Now, of course, h is a very small number, and the L, if L is a big macroscopic length of wire or something, 1 over L is a very small number. And so the quanta, the separation between different values, different allowed values of the momenta is very small. You can get, if L is large and h is small, you can get almost any number. Not almost any number, but you can get a very dense collection of possible numbers. All right? But, okay. That's the quantization of momentum in a world in which everything is periodic. Yeah.
Total momentum of the wave or per unit?
Total momentum, no, total momentum of the object. Total momentum of any quantum. Now, if every quantum has to have an integer multiple of this basic unit of momentum, then any number of quanta also have to have an integer multiple of it. All right? You might have, each quantum is identified in terms of its value of n, in terms of its momentum. But there are allowed momentum and disallowed momentum. The allowed momentum are discrete multiples of a basic unit, and any number of photons, electrons, and so forth necessarily come in these discrete multiples. This is
why do we have to have stationary model when you come back to the same point? What is it?
That's the assumption. Well, that's the assumption that that the space is really genuinely periodic. That there's nothing special about any point. And it is a fair question. It is a good question. But it's also the assumption that, for example, the electromagnetic wave, electric field, is a observable quantity and it doesn't have sudden jumps in it. In fact, a sudden jump, you would have, if it didn't come back to itself, it would have to make a sudden jump at this point. A sudden jump is very costly in energy and in momentum. So sudden jumps in fields are continuous things. They're not allowed to jump like that.
What if you had a packetized wave?
If you have what?
What if you had a packetized wave traveling around?
A what kind of wave? Packetized. Oh, that's all right. Any packetized, that's a good word. Any packetized wave, that's a packetized wave, is a sum of individual plane waves, sines and cosines. That's the Fourier analysis. The statement, the real statement is any allowable wave is a sum of waves, each of which has this discretized possible values of momentum. So it's a statement about Fourier transforms, that the Fourier analysis of any allowable wave only has these discrete multiples of the basic unit of P. Okay.
So is there a problem when L gets very, very, very small?
Yeah, the smallest momentum gets very, very, very big. How small is very small?
Approaching zero.
You don't want to get smaller than the Planck length. That's a bad thing to do. Up till that, no, there's no problem. We could, yeah, let's pursue this a moment. Something that's not in my notes, but let's pursue it. It's important. Let's really imagine now that we genuinely have a particle moving on a genuine circular wire. For fun, let's really now take a bead moving on a really circular wire and see if we can understand what this quantization of momentum means in another language. Let's take the circular wire to have a radius r. Okay. Let it have a radius r. Oh, I erased the important equation. What was the important equation? The important equation was the allowable momentum is equal to an integer times h over lambda? Over L? Over L, right? Okay. Now, the radius of the orbit is r, and that means that P is nh over 2 pi r, right? You can see by now that h bar would have been a better choice in this equation, right? Let's leave it, and later on we'll put back h bar. Okay, that's the momentum, and the momentum is quantized. Every single electron, photon, or anything else has to have an integer multiple of this. Now, what about the angular momentum? What's the relationship between momentum, radius, and angular momentum? For a circular orbit, for the simplest possible orbit. Yes, it is MVR. Well, for a non-relativistic particle, it's MVR. MVR. L stands for angular momentum. MVR. But what is MV? P. So it's P times R. Now, MVR is not completely general. For a relativistic particle, the momentum is not m times v. But angular momentum is equal to momentum times distance is very general. That is, for a particle, that is the definition of the momentum, at least for a circular orbit. For other orbits, it's the cross product, r cross p, but it's always r times p. And so now look at this. What this says is that r times p multiplied by r, angular momentum, is an integer multiple of h divided by 2 pi, or an integer multiple of Planck's other constant. All right, so momentum is another quantity which is, angular momentum is a quantity which is quantized, but always in the same unit. Unlike the momentum, Here the momentum is quantized in a unit which depends on the angular, on L. Whoops, did I use L for two things? Excuse me. What shall I call angular momentum? Angular momentum, AM. We'll eventually change that. I don't like that, but for the moment, angular momentum, all right, is n times h bar. Momentum is quantized in this periodic world, but the unit of momentum depends on the length around the circuit, okay? The angular momentum is quantized, but always in units of h bar, okay? All angular momenta come in units of h bar except when they don't. When they don't is when you have fermions, but we'll come to that. That's later, not tonight. Okay. There are exceptions to this rule. Okay. Now we want, in the next hour, to invent the idea of a quantum field. And what is a quantum field? In the simplest possible case, the simplest possible situation, what exactly is a quantum field? How is the quantum field related to particles and to its quanta? What is the connection between particles and fields with some precision? And that's what we'll do next, but let's take a 5-minute break. All right, now we have to enter into the real world of quantum mechanics a little bit. And for that, if you're not knowledgeable about it, you have various alternatives. One is to go to sleep. Another is to listen and try to get, sort of a, what's the right word for a very impressionistic, what? Yeah, get the, there must be some word for very impressionistic, sort of soft, fuzzy feel for things. And the third is to go back, what?
Fox News.
I hope to do better than that, please. And the third is to go back and learn a little bit about quantum mechanics. There will be nothing here that I haven't discussed in previous lectures on quantum mechanics. And in particular, the most important thing for our purposes now is one of the simplest of all quantum systems, the harmonic oscillator. Why does the harmonic oscillator come up? The harmonic oscillator is important for a great many reasons, but in our particular context, it's because waves are oscillations. If you just see a wave going past you, obviously the field, electric, magnetic, whatever it is, oscillates. In fact, the fact that it oscillates is equivalent to the statement that it has a frequency. A wave may be made up out of a superposition of many different wavelengths. For example, light, you can mix together different colors of light and create light of mixed different wavelengths. But you can also separate it, as did Newton, into its component wavelengths. And so every light wave can be thought of as being made up of individual components, each with its own frequency, its own amplitude, and so forth. Therefore, it can be thought of as being made up out of a collection of quanta, and the quanta are not all of the same energy and momentum, but still it can be separated into quanta of different energy and momentum. And each energy and momentum is associated with a wavelength. Each wavelength is associated with a frequency, and a frequency is by definition an oscillation. So one can think of a wave as a collection of harmonic oscillators. Harmonic oscillators being the simplest kind of oscillation, sines and cosines. In order to proceed with what a quantum field is, we have to go back to what the harmonic oscillator is. So let's begin with the harmonic oscillator. Quantum mechanics is a strange theory. It has things, numbers in it, which don't satisfy the usual rules of arithmetic. Technically, they are operators representing the observable things that you can measure. And they have some rules. You can add them, you can multiply them, but they don't necessarily commute. What does that mean? That means if you have two variables describing two different attributes or properties of a system, each of which by itself might be measurable, might be something you can measure. Let's call them A and B, just to give them names. A could stand, for example, for electric field. B could stand for magnetic field. Or A could stand for the position of an electron. B could stand for the electric field. But any two pair of things, then ordinarily, in ordinary mathematics, of course, the product of them doesn't matter which order you multiply them. A times B is equal to B times A. That's just a property of numbers. In quantum mechanics, of course, that is not generally true. It may or may not be true of two observable quantities. And when it's not true, we just write that the difference between these is not equal to 0. Now, what nonsense. I mean, if I measure the electric field and it's some number, and I measure the magnetic field and it's some other number, and I multiply them, how can it possibly be that it doesn't make sense to multiply them in the opposite order and get the same answer? Generally speaking, when the answer depends on the order of multiplication, what it really means, in other words, when this is not 0, what it really means is that you can't measure both of these things simultaneously, that they interfere with each other. The experiment that measures one of them necessarily screws up the measurement of the other one. And in that sense, there's no contradiction. When this is not 0, simply means you can't measure both of them together. When you can measure two things simultaneously, and you measure them, you get numbers for them. When you multiply the numbers have to commute. It doesn't matter which order you multiply them in. And so the test for whether you can measure two things at the same time is whether this quantity, which is also called the commutator, AB minus BA, is called the commutator of A and B. Commutator, you know, like going back and forth, going to work and back. You interchange the order of them. It's labeled by a bracket with a comma. In A and B, the order matters, so typically this is not equal to 0. Incidentally, the commutator of B with A, that's just exactly the same thing except in the opposite order. And that's just a sign difference. These two are the same except for a sign. Okay, that's quantum mechanics in a nutshell. We just did quantum mechanics. Examples. Now, I'm not proving this. I'm just telling you this now. But nevertheless, it's a fact. Partly empirical fact, partly mathematical fact. A particle has different components of position. X, Y, and Z, for example. You can measure the position of a particle. So the components of position of a particle are candidates for things which are observables. These things commute with each other. You can measure the X and the Y of a particle at the same time. You can measure the X, the Y, and the Z of a particle, all three simultaneously. What else can you measure about a particle? You can measure its velocity or its momentum, mass times velocity. And those things are called, the components of them are called px, py, and pz. They're the components of the vector momentum. And they also commute with each other. You can measure the three components, or better yet, the magnitude and the direction of the momentum. But you can measure all three components simultaneously. There's no obstruction. They commute with each other. So x commutes with y, commutes with z. Px commutes with py, commutes with pz. But the components of position do not commute with the components of momentum. So, for example, you cannot measure the position, the x component of the position of a particle, and the x component of the momentum. Every time you try to measure the x component of position, you will give the particle a whack and change its momentum, and the result is you can't measure both of them. This is not equal to 0. It's equal to I times Planck's constant. It's small, simply reflecting the fact that, well, the uncertainties in position and momenta are small and of order h bar. Likewise, for the y components, the y position and the y momentum don't commute with each other. Same for the z components. How about x with the y component of momentum? Can you measure x and the y component of momentum simultaneously? Yes, as a matter of fact, you can. That may not be obvious, but it is true. Okay, so that's another aspect of quantum mechanics. And now let's consider the harmonic oscillator. Now, I'm telling you facts for the most part, but I'll try to put the mathematical facts into some kind of context. These are the facts that we went through previous quarters, so I'm not going to derive them. I'm just going to state them.
Just one quick question.
Yeah.
When we go from x to y, isn't it conventional to go I to j?
No. This is the square root of minus 1. This is not ij. This is not ij and k, which are unit vectors along the 3 axes. No. And they're also not quaternions, which also have an ij and a k associated with x, y, and z. But no, just the square root of minus 1. Where does the square root of minus 1 get into a formula like this? Don't ask. We're not going to need it. The fact is we won't really need it. We just need to know that algebraic manipulations in quantum mechanics are a little bit funny. And the funniness is that you can't, as a rule, interchange the orders of our operations.
Sir?
Yeah. Yeah.
AB minus BA. That means first measure A, then...
It doesn't mean measure. It doesn't mean measure. Forget measuring. These are simply mathematical manipulations which are, yeah. It doesn't mean first measure A and then measure B. It's simply not simply, it is a mathematical manipulation that it's matrix multiplication, operator multiplication, yes. But we're not going through the principles of quantum mechanics here. I'm just restating things that we've learned in the past. And if you need to understand them better, the only way to do it is to go back to earlier lectures. Okay.
Question?
Yes, sir.
Does that apply to a photon?
Hmm?
Does that apply to a photon?
Not
Some sense.
quite, but close. It doesn't really apply to a photon. It applies, strictly speaking, to non-relativistic particles. The problem is that the position of a photon is not so well defined. The position of a photon is harder to define than the position of a non-relativistic particle. But we can come back to that. That's a subtlety which is not terribly important to us now. Okay, the harmonic oscillator. The harmonic oscillator is a system, a classical system, which has a quantum mechanical analog. And it simply means a system which oscillates, a weight on the end of a spring which oscillates up and down, a sound wave that oscillates, a light wave that oscillates, anything that oscillates like a spring going back and forth. We can think of thousands of examples, and the mathematics of them is always the same. Every oscillation or every oscillator has a frequency. It can either be taken, and we can call it an omega. The frequency, again, is 2 pi times the number of cycles per second. All right? Cycle per second for a spring with a weight on it is just how long it takes to go through one full swing and come back to the same place. Not just the same place, but the same velocity. So if you have a weight on the end of a spring and it oscillates, the frequency is not how long it takes to come back to the same place, but how long it takes to come back to the same place moving in the same direction. So one full oscillation is the period. The number of cycles or number of oscillations per second is the frequency f, and as usual, omega is 2 pi f. Nothing unusual, the usual omega. Now, what is unusual about the quantum mechanical harmonic oscillator is that energy is quantized. Not momentum, but energy is quantized. Right, this is something which you'll either look up or accept. So let's plot vertically the energy levels of such a harmonic oscillator. Classically, of course, there is a lowest energy, which is 0, just the oscillator at rest. And then you give it a little poke and it starts to swing back and forth, and you can give it any positive value of energy. Of course, if you hit it too hard and try to give it too much energy, you might melt the spring or break the spring. But in a mathematically idealized version of the harmonic oscillator, you can give it any positive value of energy. Not so the quantum mechanical oscillator. The quantum mechanical oscillator has discrete integer units of energy. If we call the lowest energy 0, sometimes it's appropriate to call the lowest energy not quite 0, but we can define. We can define the lowest energy to be 0, then what's the next energy level? H bar omega. The same formula as the energy of a photon of frequency omega. What's the next one? 2h bar omega. That could either be the energy of a single photon associated with a frequency twice as big as the first one, or it could correspond to 2 photons, both associated with a wave of frequency omega. It's the second idea that I want to dwell on, that this has the same energy as 2 photons. Now, so far there are no photons. There's only springs and balls and oscillations back and forth. But nevertheless, this does have the energy of 1 photon associated with a frequency omega. This has the energy of 2 photons of frequency omega, and so forth. 3 h bar omega, and so forth. Those are the possible energies of the harmonic oscillator. Okay? Nothing in between. We can label them with an integer, and we can write that the energy is an integer times h bar omega, where n is just an integer which labels which one of these states the oscillator is oscillating in. It's just a matter of notation. For us here, it's just a matter of notation. Mathematics of it, we don't need to get into. We label the various states of the oscillator by an integer n, and it's conventional to just label the states of the oscillator by a little pointy thing like that. It's called a ket. It's called a ket because it's the right-hand side of a bracket. But we don't need the bra end of it. We only need the ket end of it. Right? And it's, as I said, go back and study quantum mechanics. But all this labels This is a symbol representing, if you put n equals 0 here, it represents the state of the oscillator where it's in its ground state. Ground state means the lowest energy state. If you put a 1 here, it represents the oscillator oscillating with 1 quantum of energy, 1 unit of energy. You put a 2 here, it represents the oscillator with 2 units of energy, and so forth. Right? So it's just a notation. It's just a convenient notation for labeling the various possible configurations of the quantum harmonic oscillator. Now, let's invent an operation. It's actually not only an operation, it's an operator. There's a difference. An operator. And this operator acts on a state to change the state to a new state. So a mathematical operation which takes you from any state to the neighboring one 1 unit above it. Acts on this state to give you this one. Acts on this state to give you this one. Acts on this state to give you this one. Acts on this state to give you this one. So we can write down what it does. Let's call it a plus. And the plus indicates that it raises the energy of a state. And it acts on the nth state to give what? N plus 1, but with a coefficient in front of it. Square root of n plus 1. Now this is mumbly-jumbly unless you know the bit about the mathematics of linear operators and so forth. So as I said, either you know it and you can follow it, or you don't know it and you can just get a hazy impression of what it means. But this is the mathematical property of this operation here. It multiplies any state vector by a square root of n plus 1 and raises you to the next level. But basically, it's a shift, a thing which shifts you from one level to the next. It's just an operation which shifts you from one level to the next, and we've got to keep track of a numerical coefficient in front of it. What about a minus? What does it do? Takes you down, and minus 1, well, what's the coefficient? Square root of n. Square root of n. What happens if this one acts on the bottom state? Where does it take you? It doesn't take you anywhere. It just gives you 0. That's because if it acts on the bottom state, n is 0, and it just gives you 0. Nothing. No state there. Just the non-state. There's nothing to get to, so it just gives you 0. All right, this is the mathematics of creation and annihilation operators, or raising and lowering operators. Now we're gonna do some little mumbo jumbo with it. I'm going to show you some properties of these operations. They're interesting, they're entertaining, and you can do some, you can have some fun with them. Just knowing some very simple set of rules. And this is the rules. Let's see what happens if we take the state n and multiply it first by a minus and then by a plus. In other words, let's hit it with a minus and then a plus. What do we get? Okay. All we do is follow the rules. All right, so first of all, one important thing. Some things are just numbers. Not everything is one of these peculiar things that, where the order of multiplication matters. Some things are really just numbers. Things like n are just numbers. That means that the order that you multiply them doesn't matter. Some things, the order of multiplication is perfectly ordinary, and n is always something rather ordinary. Okay, so what happens what happens, what is this equal to? Well, let's take it in pieces. Let's first multiply a minus by n. What does it give? A plus, and then a minus times n is what? Square root of n times n minus 1. So let's take that on the outside, and n minus 1. Now what happens if we hit it with a plus? If we hit any vector, or any state with a plus, it raises us back, it raises us to the next level up, but multiplies by square root of n plus 1. But what does square root of n plus 1 here mean? It just means square root of n. Since I'm now starting at n minus 1, hitting it with a plus will give me square root of n, another square root of n, and n. Square root of n times square root of n is n. It just gives me the number n times n. That's just a little game that we're playing. We're playing a little game with a set of logical rules here. And what we find out is if we multiply by a plus and a minus with this set of logical rules, it's equivalent to multiplying by the numerical number n. Whatever state we put here, if we put here the 0th state, or if we put here the lowest state, we get 0. If we put here the first state, we get 1. If we put here the second state, we get 2, and so forth. So whenever we do this combined set of operations, it picks out for us the numerical level and tells us which level we're at. If we want to find out which level we're talking about, I may not know what it is. I may just call it by some other name, bloopus. We just put bloopus here, and we want to find out what n bloopus corresponds to. Well, we multiply it by a plus times a minus, and we find out what the numerical coefficient is. That numerical coefficient tells us what level of the oscillator we were playing with. Okay? So we can write this in another way. We can simply write that multiplication by a plus times a minus is the same as multiplication by n. But what is n? N is simply the energy level. Well, not quite. The energy level, we need something else. We need h bar omega. We need to multiply by h bar omega. So we can write n h bar omega is h bar omega times a plus a minus. And what does that tell us? That tells us that the energy of the oscillator, if we didn't know what the energy of the oscillator was, we could find out mathematically, not as a matter of empirical experiment, but as a matter of playing this logical game, we could determine what level we were talking about by taking the state, unknown state, and multiplying it by a plus a minus times h bar omega. Now, this is a little game, as I said, and doesn't correspond to any actual experiment, but in fact, this is the actual energy of the oscillator. Okay, so that's a mathematical bunch of tricks, bunch of trickery. Let's multiply them in the opposite order. All right, so what did we find out? We found out that a plus times a minus is equal to n, meaning to say that if you do this operation on any state, it just multiplies by n. What about the opposite order? Let's try it in the opposite order. Using the same little logical rules, a minus times a plus on n. What does that give? Did I do that right? A minus times a plus. The opposite order. So what does a plus give? This gives square root of n plus 1 times n plus 1, right? And now let's multiply that by a minus. A minus will bring you back down to n, but it will give you another factor of square root of n plus 1. Right? Whenever a minus acts, it gives you the numerical coefficient, which is the same as the thing inside here. So that gives you square root of n plus 1 times square root of n plus 1 again, times n. Brings you back down, but gives you the factor, overall factor of n plus 1. So what did we find? We found that multiplying in the opposite order gives us different answers. Almost the same answer, but not quite. In one order, a plus a minus is n. In the other order, a minus times a plus is n plus 1. So with this little bit of logical gamesmanship here, or mathematical symbology, we find that the order of these two operations isn't the same. Well, what does that mean? Does that mean that a plus and a minus, that if we were to measure them and then take the values that we measure for them, the numerical values, whatever they are, whatever they correspond to, we measure them, that when we multiply their values by each other, they don't commute? Well, that doesn't make sense. Numbers always commute when we multiply them. What this means is that whatever a plus and a minus correspond to, you can't measure both of them simultaneously. Now, what they correspond to is a combination of the amplitude of this harmonic oscillator, how big the oscillation is, and its phase. Its phase, does everybody know what the phase of an oscillation is? It's basically the time at which the oscillator passes through the origin. The oscillator can oscillate back and forth, or you can delay it a little bit so that it goes through the origin at a later or earlier time. You can't, whatever A is, you can't measure it, A plus and A minus simultaneously. That's what this tells you. That's all it tells you. That they don't commute, and therefore they're not simultaneously measurable, but they're still interesting mathematical little objects. What do they do? What do? They are mathematical operations which raise you up and down this tower. What do? They add and subtract quanta of energy of the oscillator. Okay. Now, if the oscillator happens to correspond to an electromagnetic oscillation, an oscillation of the electromagnetic field, then what these operators do is they add and subtract photons. They add and subtract photons. They are what are called creation and annihilation operators. All right, so let's...
Question?
Yeah.
Does that correspond to any physical experiment that we could talk about?
Well, you can measure the number of photons, but you can't measure the A plus and the A minus separately. Yeah. It's an interesting question of whether you can measure A plus or A minus individually, and the answer for technical reasons is no, but this doesn't tell you that. Okay. All right, so we have the idea now of operations or mathematical quantum mechanical operations, which would make no sense classically at all. We wouldn't multiply states by operators like this, but quantum mechanically, we have the idea of creation and annihilation operators, mathematical operations which add and subtract quanta of energy for a fixed frequency. Right? Now, when we have a system which has many oscillators, you can imagine we have many springs with many balls hanging off them of different frequencies. Or you can imagine electromagnetic waves in a cavity. Each different wavelength has a different frequency. We can excite them independently. We can excite one wave, we can excite another wave, excite them independently. Then we have a system which contains many different oscillations with many different frequencies. That means to describe, this may be a good place to slow down a little bit. This, of course, is a little bit indigestible unless you've seen it before. Okay. How many people have seen it before? When?
We were in the other room. I don't know.
No, of course I gave a lecture in another course. Yeah, right. I give many lectures on it probably by now in this.
Oh, in this course you gave another
in this course, I have not talked about this yet. By this course, I mean this sequence. Oh, the sequence, of course, yes. We've talked about it many times, I think. But it certainly is in the lectures on quantum mechanics.
It may not have been recorded because we had to move to a different room.
It wasn't recorded?
It may not have been because we were in a different room. And I don't know whether they set it up or not. We were in the next room over.
No, it's okay, just move on.
Yeah, okay. The harmonic oscillator is the most basic quantum mechanical system. Please learn it if you want to follow these lectures. And it is, you know, you can see where it's going. We describe particles as oscillations, and we create and annihilate particles, put them into the system, take them out of the system by mathematical operations that are these creation and annihilation operators. So they're absolutely central to the understanding of quantum field theory and particle physics, just completely. Okay, let's come back very quickly now, and I think we'll have to discuss this again. But let's come back to this little model of a world on a circle, where we made the world finite by making space to be a circle instead of an infinite line. And now it's a very simple world of only one dimension, but we have this line. Distance around it is L. Let's imagine photons or electromagnetic radiation or whatever kind of particles moving on this line. There are some allowable values of the wavelength. Remember, what the allowable values of the wavelength are L divided by n, where n is any integer. Okay. That means there are allowable values of momentum. These are allowable values of frequency and allowable values of momentum. Okay. Those allowable values of frequency we can call omega n. N goes from minus infinity to infinity, whatever it goes over. Well, n goes from 0 to infinity, all the possible values of frequencies. Right? The waves moving on this system here are a collection of harmonic oscillators. One harmonic oscillator for each value of n, for each frequency of oscillation. You can add energy independently to each frequency. Right? You can take any given frequency and add energy to oscillations in that frequency. You can then add energy on top of that with some other frequency. Right? So a system of waves moving on a circle like this, or moving in anything for that matter, is really just a collection of harmonic oscillators with a certain set of allowable frequencies. The question is, how do you describe this system mathematically in quantum mechanics? And the answer is, let's begin with the idea of a state. We're not going to do this in detail now. We're not actually going to get to our first example of a quantum field. We'll get there next time. But let's work around it a little bit. How would we label the states of a system where there are many oscillators around? You can either think about this as all the oscillations of a wave on a circle, or you can just think of it as a bunch of balls and springs with different frequencies. How would you label it? Well, each harmonic oscillator has a quantized energy. The quantized energy for each one of these oscillators is some integer times omega n times h bar. So what we have to state then is the integer excitations of each oscillator. The number of quanta with the lowest frequency whatever it is, or n1, the number of quanta with frequency n2, or the number of quanta with the third frequency, and so forth. All right. And on for infinity, forever. This would correspond to a state in which the lowest wavelength, or the longest wavelength oscillator has N1 quanta in it. The next longest wavelength oscillation would have N2, N3. I'm getting a little bit tired, and I suspect you are also, but what I want you to think about is the guitar string or the violin string, and how you how you create harmonics. What we're talking about is harmonics. All right, so there's an overall mode of oscillation of the string where it behaves up and down like that. If we forgot everything else and just thought of this as a simple harmonic oscillator oscillating back and forth, we could say that the energy level of the system is just one, possibly no excitations, 1 unit of excitation, 2 units of excitation, 3 units of excitation. And how much would each unit of excitation cost? It would cost an energy which was the frequency of that particular note, omega, times h bar, times the number of oscillations with that frequency. Then we could add additional energy in the form of the first harmonic. All right, so if this oscillation corresponded to middle C, this oscillation would be what? C 1 octave above middle C or whatever. Add some energy in that. That has twice the frequency. Twice the frequency, so we would be then adding a number of quanta with the second frequency. And then we could add oscillations on top of that. I always have trouble drawing this next one. I can't draw it, you know what I mean. 3 with 2 nodes, 2 nodes, but it would have 3 times the frequency, right? 3 waves fit in. That has an oscillation like that has 3 times the frequency. And how many oscillators, how many quanta would we put in? Well, we can put any number in, but that would be N3. And the entire configuration of this oscillating string, quantum mechanically oscillating string, would be characterized by a collection of integers which tells us how much quantized energy there is in each mode of oscillation. So basically what we have to do mathematically is repeat the mathematics of the harmonic oscillator infinitely many times, 1 for each mode of oscillation. The result is a quantum field. That's what a quantum field is it's a collection of harmonic oscillators, a collection of creation and annihilation operators which add and subtract energy in each mode of oscillation. And it's the mathematics of that collection of oscillators which is called quantum field theory. So if we want to carry on with this subject, we have to get used to this language. Okay. Let's quit here. Well, let me just say one more thing. If we're interested in particle physics experiments, what happens in particle physics experiments? Particles with given energy momentum come in. They rearrange. Particles with other energy and momentum go out. So in other words, we remove particles from the initial state and replace them by particles in the final state. The mathematical description of that is to remove particles with annihilation operators and replace them with particles of other momenta and energy involving other creation and annihilation operators. So that's what these operators do. They remove particles and put particles in, and the mathematical description of the creation and annihilation of particles is through these kind of mathematical symbols. That's why they're so important. Yeah.
Yeah, the in is used to like indicate the energy level, but then it's also used to indicate the count of number of quanta. Is that right? I mean,
there are two integers going on here. One integer has to do with the number of nodes here, and the other has to do with the number of quanta. I'll spell this out again. There are two distinct integers. In this example, the number of nodes would tell you the frequency, and then the number of quanta with each frequency. So there are two integers floating around. Yeah. Yeah. Right. One of them is associated with the, yeah. This is hard stuff. This is not easy. It's abstract. It's too abstract.
For more, please visit us at stanford.edu.